We're solving problem 8 from the 2025 AIME2. For an unlimited supply of 1-cent coins, 10-cent coins, and 25-cent coins, Silas wants to find a collection of coins that has a total value of n cents, where n is a positive integer. He uses the so-called greedy algorithm, successively choosing the coin of greatest value that does not cause the value of this collection to exceed n. For example, to get to 42 cents, Silas will choose a 25-cent coin, then a 10-cent coin, then 7 1-cent coins. However, this collection of 9 coins uses more coins than necessary to get to a total of 42 cents. Indeed, choosing 4 10-cent coins and 2 1-cent coins achieves the same total value with only 6 coins. In general, the greedy algorithm succeeds for a given n if no other collection of 1-cent, 10-cent, and 25-cent coins gives a total value of n cents using strictly fewer coins than the collection given by the greedy algorithm. Find the number of values of n between 1 and 1,000 for which the greedy algorithm succeeds. So we have any number of 1-cent coins, 10-cent coins, and 25-cent coins. The example they give you is 42 cents, right? So this is basic. They're teaching us how the greedy algorithm works. So we have total sum of 42 cents. So you have to start from the biggest cent value, which is 25, and you want the greatest number of that biggest cent value first. So you can only have 125, and then you move to the next lower denomination, which is in 10 cents. You can, again, only have one 10-cent without going over 42. And then for here, you have to have 7 1-cent coins, which is not optimal because you can have 4 10s and 2 2s. Now, usually in these problems with these algorithms and equations, and you want to find how many values succeed between a very large range, say 1,000 numbers, 500 numbers, 100 numbers, there's usually a pattern. And again, what we're going to do is try to find a pattern and see if there is a noticeable pattern, and there should be usually in these problems. So what we can do, we first note that if the sum n is less than or equal to 25, the greedy algorithm automatically succeeds. But then we can start considering ranges, right? Like 25 to 30, they obviously succeed. But once you get to, you notice cracks starting to form here at n is 30 to 34. Because the optimal greedy algorithm way to get 30 is, well, you have to start with the largest. So 25, and then you can't have any 10s since it would go over 30, so you have to add 5 1s. This clearly is not optimal because the more optimal way, you could just have 3 10s. Again, you see at n from 40 to 44. There's the dash, 40 to 44. You see here that greedy algorithm says to get 40, you have a 25 plus a 10 plus 5 1s. Again, this is not optimal because you could just have 4 10s and that'll solve all your problems. So, but eventually, you see here that for every 25 values of n, we see that there are 10 values that do not work. So we therefore want to find the number of cycles of 25 such that we can compute how much don't work and then subtract that number from 1,000 to get our desired numbers that work. So in order to calculate that, we do 955 minus 30 over 25 plus 1 for the starting values we already have. This gets us to 38. 38 cycles of 25 where 10 values don't work. Since we want to use complementary counting, we need to find the number of numbers that don't work. So since there's 10 numbers that don't work in every 25, we do 38 times 10, which is 380. Now, this is when we're not considering the range, n is 980 to 1004. If we're considering that range, then there are some cases, there's two actually, that don't work. So we have 980 to 984, and 990 to 994. These both grant us 5 each, so we have 10 here that don't work. So we should add the 10 to the 380. So 10 plus 380 gives us the total number of numbers that don't work, or 390. So then we have the number of numbers that don't work. We can do the amount of total numbers, which is 1,000, subtract the number of numbers that don't work, which is 390, to get the number of numbers that work, which is 610. And this is our answer.